This is a general theorem. Okay, so to prove this, and we will go through the proof because I think the techniques that we use in this proof are things that are useful to us, and we'll see sort of those pieces in some of the other parts of today's lecture. But if we want to prove this, then we have to prove both directions. So let's first of all prove that if this integral is finite, then the system is bounded input, bounded output stable. All right, so from what we did last day, we know the relationship between y and u. So y of t is the integral from minus infinity to t of h of t tau, u of tau, u tau. Right? That's our input-output response based on this weighting matrix, weighting pattern, weighting function. Okay, so we can take the norm of both sides of that. So if we look at the norm of y of t, and I'm just applying any norm here. So take the norm of both sides, bring the norm under the integral, replace this with less than or equal to, so the integral from minus infinity to t of the norm of this h of t tau, u of tau. And so this is true, I mean, I'm just using any norm. So it's certainly true for the infinity norm. We're using now the infinity norm. And I gave a little review, you remember your norms, but just on the first page of this lecture notes, you'll see a review of the norms that we're using here. So it's certainly true if I replace it with the maximum value over time. So I'm replacing this with the functional infinity norm. And then I'm breaking this up. When I break that up, as we know, this becomes the induced infinity norm of that matrix times the infinity norm of u of tau, d tau. All right, so that's just a straightforward result of taking the norms of both sides of this equation and using our bound by recognizing that the integral of the norm is greater than or equal to the norm of the integral is greater than or equal to the integral of the norm. Sorry, the norm of the integral is less than or equal to the integral of the norm. Okay, and then we do one of our standard tricks that we remember from our existence and uniqueness theorems when we use these kinds of techniques. I can replace this. So this function u of tau is dependent on tau, but if I'm looking at the functional infinity norm, so now I'm going to I can make that independent of tau and bring it outside the integral. So d tau here, and then I replace this with the functional infinity norm. Okay, which is what this is. This is the infinity norm on y. Okay.
So before you made it a functional infinity norm, it was like
when it was still under here, it was the infinity norm of u of tau. U of tau is just a vector, so that was just my regular vector norm, the infinity norm of that. Okay, but this bound still holds when I replace that with the function infinity norm, because if it's true for all tau under the integral, it's certainly true for the largest value, or the tau that gives you the largest value. Right, so I can take that outside of the integral, and so now I'm going to say, okay, this is less than or equal to some k. All right, so I'm assuming that this is finite. I'm going to call that k, which is less than infinity by my assumption of my theorem. So that's less than or equal to u. And in fact, I've written this as yt infinity. I can, the inequality is maintained if I replace that with the functional infinity norm, right? For the same reason. If this is true for all t, it's going to be true for the largest value. So that direction of the proof is fairly straightforward. So if we have that this is finite, then we see that bounded inputs produce bounded outputs. Now, the other direction we'll prove by contradiction. Okay, and so I'm going to assume, and the notation's not great, but for the sake of contradiction, I'm going to assume that this, this supremum of this integral is not finite, it's infinite. Okay, so assume, so I'm going to do this direction by contradiction. And so I'm going to assume that the supremum over t of the integral from minus infinity to t of this norm of h of t tau d tau is equal to infinity. This is where I'm being a little informal. I'm just saying it's not finite, so it's infinite. All right, so what is that? Of course, what we've got in here is a norm of a matrix. And so we have a kind of side claim, or an aside, that if you've got that the matrix norm is infinite, or the integral of the matrix norm is infinite, then that means that at least one of the elements of that matrix has to have infinite norm. Okay, so the claim that we're going to make is that, and so this will just allow us to sort of query different, different elements of that matrix. But we'll sort of state the opposite, that if the supremum of the integral of h of t tau, and we'll use the induced infinity norm, d tau, if that is finite, then that's equivalent to saying that the supremum over all t of the integral from minus infinity to t of at least one of the elements of that matrix, and I'm going to call the elements of that matrix little h ij, so that's the ijth element of this matrix H. And that's a scalar function, so I'm just going to use absolute value here. D tau is finite, and that's that has to be true. So if the matrix norm is finite, it means that the supremum, it means that the norm of all of the individual ijth elements have to be finite. So this has to be true for all I and for all j. Okay, so we're representing h, as we wrote last day, h of t tau to be our n out by ni dimensional matrix, h11 of t tau, h12 of t tau, h1 ni of t tau, blah, 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 h n out of h n out 1 of t tau. So these are all the individual elements. And there's an ij element, which we're going to call hij of t tau. And so that's generally representing an element of that matrix. Okay, so basically, and I think this is quite intuitive. We have a little proof in the notes, but the only way that you can get that the matrix norm is going to be finite is if the norms of the individual elements are finite, and vice versa. So you can see this proof in the notes. And the proof just goes by, it's just a proof using norms. Using properties of norms. See notes. Okay, so now we're saying our contradiction hypothesis is that if this is infinite, it means that there exists at least one hij for which this is infinite. Okay, so after the aside, we'll come down here and say, therefore, by this assumption, we have that there exists one, ij, index ij. So I'm going to call the index ij alpha beta. So there exists an index alpha and an index beta such that the supremum over t of the integral from minus infinity to t of h alpha beta of t tau d tau is infinite. Okay, so that's just, you know, the alpha row, the beta column. Alpha row, beta column. Is it, can you see this part of the board? Is that okay? A little bit of a stretch.
These edges.
Right here?
It's okay.
It's okay. Ever since we started videotaping lectures, fewer people have been coming to class. I don't know if that's good or bad. So, all right, so what does that mean? Okay, so now I'm going to translate this into something slightly weird. So we'll erase our linear time-varying system. And so our goal here is by contradiction. So we're actually trying to prove that if this is true, the system is not bounded input, bounded output stable. And remember at the end of last day's class, I asked you if you have the definition of bounded input, bounded output stable, what does it mean to be not bounded input, bounded output stable? So there exists an input which is bounded such that for all k, you're not going to get this kind of bound. So there exists some bounded input such that for all k, y can't be bounded to be less than k. So let me actually just write this as an aside then. So to prove that something is not bounded input, bounded output stable, aside, and it's a remark, it's actually a little earlier in the lecture notes, we'll come to it now. A system is not, L is not BIBO stable if, okay, so just sort of repeating what we said, if no k exists to satisfy this equation here for a bounded input. And so we can repose that as the following. And this is kind of a way we're going to characterize a system not being bounded input, bounded output stable. So if there exists, and the reason I want to do it this way is because so I can actually develop a proof technique for not bounded input, bounded output stable. So we say it as follows. If there exists a sequence of inputs, and I'm going to index so indexed by L, so I'll index them by L, indexed by L, and we're going to call them U superscript L of T. Okay, so these are bounded, so they belong to L infinity, it's ni dimensional. And that's for L equals 1, 2, 3, dot, 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 where the norm of those inputs is equal to 1. And the norm of the output corresponding to the Lth input is greater than L, where L is my index. So here L is, since this has one norm, here L is our k for proving boundedness. Okay, so if you give me, so L is monotone increasing, right? It's just an index. So if you give me a finite k, I can find a bigger L that will make my output greater than the k that you give me. So there's going to be no k. If this is true, there's going to be no k which will allow this to be true. And the reason we pose it this way is because if we're trying to prove that something is not bounded input, bounded output stable, we kind of have to do it systematically. We can't just say that input is infinite. We have to sort of say, okay, it's not bounded by any k. Okay, so that's why I'm developing this sequence of inputs. All right, so this kind of points to what my proof technique is for proving that if this hypothesis is true, then the system cannot be bounded input, bounded output stable. We're going to use this, this existence of a sequence. Okay, so this is an aside, but this is what I'm going to use now. So now, if this is true, so if I have that the supremum of the integral of at least one element of my weighting matrix, if that is infinite, then I have that, so continuing the proof, therefore, there exists a sequence of time, so I'll write it as T sub L, from L equals 1 up to infinity, such that the integral from minus infinity to TL of H alpha beta TL tau norm d tau is greater than L. Alright, so that's true for my L equals 1, 2, 3 up to infinity. Okay, that just comes from the fact that I assumed that it's infinite over there. Alright, so now I want to show that this is true. If this is true, then I want to show that this is true. So I've just reposed the fact that this is not finite in this way. Okay, so now I'm going to choose an input. So now I get to select a bounded input. So you just have to show existence of a bounded input that gives you an unbounded output.
So can you explain how that remark works? So why not meeting that condition makes it not BIBO stable?
Why meeting this condition makes it
Or
not
yeah,
stable?
why meeting that condition
Yeah.
is not stable?
So I'm basically saying that you know, if I've got here, I've just called my bounded input 1. All right, I can always scale it. So this is a bounded input. It has norm 1. But L is a sequence that just keeps going on up to infinity. So so all of the inputs have norm 1, so I don't worry about them. I'm just feeding them into my system, and I'm going to get an output that is greater than the index, and that index goes off to infinity. So if you try to give me some finite k, so to try to prove that it's bounded input, bounded output stable, where k is the bound between the input and the output, I will always violate your finite k by just moving a little bit further along in the sequence and making my L equal to your k, or saying my L is greater than your k.
Wait,
Right, so here,
wait, so this sequence is a sequence of functions, or?
yeah, it's a sequence of input functions that's producing a sequence of output functions. And here, L is, you know, I'm going to put it in quotes, it's RK. It's the thing we're going to try to bound the output by related to the input. Okay? So to be able to prove something's not bounded input, bounded output stable, you have to show that there exists a bounded input such that there is no k such that I can bound the output to be less than or equal to k times the norm of the input. And so this is just a mechanism for doing that. And it's a mechanism where I have my index L, which is RK, going off to infinity.
So it works only if we have infinite amount of outputs?
No, I mean, this does have it is an infinite sequence. And you need the fact that k is going off to infinity. Because you need to be able to, if you give me some huge, huge, huge k, I need to be able to say, oh, I'm just going to choose some L which is greater than your k. I can always do that if L is going off to infinity. So you do it needs to be an infinite sequence so that I can select. I just want to have a mechanism for selecting a bound which violates the bound that you try to give me.
So in this condition, not only can you scale the norm of u, you can also scale the norm of y.
Yeah, I chose not to scale the norm of u. I chose to keep that at 1.
But even if you keep that 1, you can still scale the norm of y, right? So you can have like 1/2 L or 2L.
Yeah, exactly. It doesn't change it at all. I just want to be able to have a mechanism for choosing something that's greater than whatever finite k you give me.
So you say we can kind of scale the outlet norms. Is it particularly important that they be kind of regularly spaced by the index, or could it be like any?
No, I just chose something like this. You could have chosen something else which had this property. Just, I mean, it's easier like this, right? It's the simplest possible thing we could have chosen.
What is the sequence of these T sub L's?
Yeah, because I want to be able to now, you know, I want to be able to actually use this result. Okay, so now I'm taking what I know. So all I've assumed by my contradiction hypothesis is that this is not finite. So that means that there's at least one of the elements of the matrix has this being not finite. Now I want to be able to kind of construct this. I want to construct the counterexample. And so I'm going to translate, I'm just taking that result there, and I'm translating into something that will allow me to use this. It will allow me to construct this sequence. And so we'll see right now what I'm going to do with that. So you can see me starting to construct a sequence here that's going to relate to what I need to do here. So this is a little artificial because of what I need to do. So now I'm going to choose a sequence of inputs such that their norm is 1. And so U sub L of t is going to be equal to, it'll be equal to a vector that where all of the elements are 0 except the beta'th entry. And the beta'th entry, so beta is the column, where this infinite, this h that gives us an infinite integral of its norm. So the beta corresponds to that beta. So the beta'th column, or the beta'th row of my input vector is just the sign of h alpha beta comma TL T. Okay, so the sign is just something that's 1 or -1 depending on. So if this is positive, the signum gives you 1, and if it's negative, the signum gives you -1. So something that has norm 1, and the rest are zeros. All right, I did that so I can satisfy this norm being 1. So that's the beta'th entry. Everything else is 0. And that's true for t, so I have a t here, minus infinity is less than or equal to t is less than or equal to TL. So that just, okay, we'll see what it does. And this is going to be 0 if t is greater than t. So the 0 vector. Okay, so you can imagine this funny looking vector, but it's a bounded input, right? And it's got, it's actually a bounded input that has norm 1. All right, so why did we choose it this way? Well, what happens when you take this matrix and you post-multiply by this vector? All it does is it pulls out the beta'th column of your H matrix. Everything else is 0. So we have this norm of, so we're dealing with the infinity function norm. So the norm of UL is equal to 1 for each L. And if we look at the output, so it's the alpha beta'th entry. So I've applied the input to pull out the beta'th column of this matrix H, and I look at the alpha output. Okay, so this is the this is the element, the alpha element of the output vector. That evaluated in TL for that input is just the integral from minus infinity to TL of the norm of H alpha beta TL tau d tau. Right? And I did that, so I constructed the input that way because I know that this is, well, I know that it satisfies this property. Okay, so that means that if this is true for the alpha element, then it's certainly true for the norm of the vector y. L is greater than or equal to the absolute value of y alpha element, which I've just computed on the above row, which is greater than L. Right, so I've constructed a bounded input such that there is no finite k such that the infinity norm of the output as a function is less than or equal to k times the infinity norm. Intuitively, I think you guys get it, right? That if there's one of the elements of this matrix whose integral of its norm goes off to infinity, then that's going to cause a problem in the input-output relationship. What we've done here is we've just built a structure around that to make that formal. All right, so we can equate now. These are equivalent conditions that that this being finite means that the system is bounded input, bounded output stable. So this is hard to compute in general. I mean, we're taking the integral from minus infinity to t of the norm of this matrix. It's a time-varying matrix. Again, it's something that's hard to compute. But it gives us, I would say, it enables us to have a proof technique for more specific systems, which we'll see right now.
Kind of getting a little bit confused here. So we're multiplying, we're having like h times u, right? So wouldn't that be a vector? Instead of a scalar, or like instead of like one term. So wouldn't it be like, instead of h alpha beta, wouldn't it be like an entire?
Yeah, but everything else here is 0, right? And so you've, and this is a scalar here, right? I'm pulling out the alpha entry of the vector y,
Oh,
right?
yeah. That was the whole.
No, so this is the alpha entry. So that was the beta entry of u, and this is the alpha entry, or alpha component of y. So if that's true for the alpha entry, then it must be true. Here we're back at the vector. So the first place where this is used is to prove the maybe more familiar result for time invariant systems. And that's that what this translates to in terms of time invariant systems where we can compute the transfer function matrix is it allows us to prove the result that a lot of you who've seen undergraduate control before know that bounded input, bounded output stability is equivalent to saying that the poles of the transfer function are all in the open left half plane. All right, so this is what we proved in class is the more general result. But if we now specialize to the case where we have a time invariant system, we computed last day what the weighting matrix looked like for a time invariant system. But the theorem, again, we stated this last day, but now we can prove it directly from the result that we just had, is if we write out the transfer function matrix for the time invariant case, then stability of L is equivalent to, so let's just first of all write out what the weighting matrix condition looks like in the time invariant case. It means that C e to the a t b, it becomes a lot simpler in the time invariant case. dt is finite, and that's equivalent to saying that all of the poles of the transfer function matrix are in the open left. Right, and the proof of this is really just a specialization of the proof that we've just done. I'm going to leave the proof for you to take a look at yourselves. The technique actually, I'm going to leave it as an exercise. It's there, but you should go through it and make sure you understand how to apply the proof we've just done to the special case. Yes?
For this proof here, we got to the end. Where did the contradiction happen?
Well, the contradiction was, so what we were trying to prove was that if that integral of the norm of the weighting matrix was infinite, then the system is not BIBO stable. So we started out with that hypothesis, and then we got down to this condition here, which means that I've found, since I've got this condition here, that implies, let's just say the last step, that I have a, well, we'll say it in words, I've constructed a bounded input such that there is no finite k such that the infinity norm on y is less than or equal to k times the infinity norm of u, which is the condition for being not bounded input. Because of the sequence that I've set up, if you liken L to k, then if you give me some finite k, I will always just go a little bit further in my sequence and find some L that's bigger than your k. Okay, so you can go through that proof. There's, I mean, we've just gone through the more general proof, and moreover, we're going to switch now to talking about internal stability, and one of the proofs that we'll look at in internal stability is very similar to this proof. So I'd like you to take a look at that proof, go through it, but let's move on to internal stability, or often called state space stability, because it relates to the behavior of the state, which is somehow, you know, like the state gives you this internal description of the system, whereas the input-output is really just, you know, what you're able to affect using an input and what you're able to see from the output. You don't actually see necessarily all of the state behavior. Are there any questions about this proof that we've done?
Just to be clear, we used our hypothesis from the contradiction when we constructed the sequence of TLs, right? Since the integral goes to infinity, you can always just choose another TL where it stops off at some value.
Yes, yeah, exactly. So that led us immediately to the ability to construct that TL sequence. Okay, so state space stability, or internal stability. Without an input. Let's just look at x dot is equal to a of tx. And we're going to look at state space or internal stability. And usually when people talk about stability, they mean this notion of stability. So if it's input-output stability, people will say input-output stability. But if they just say stability, they mean this, or they should mean this. That's, you know, this is the more general concept of stability. Okay, so we know that the state trajectory, we know what it is in terms of the state transition matrix of the system. There's no input, so it's just a function of the initial state. We define an equilibrium point of the system to be a value of x, e, such that x dot at e is equal to 0. All right, or the 0 vector here. Okay, so if you plug in e here, it's in the null space of a of t for all t. Okay, so in this case, 0 is always an equilibrium point of this system. It's always in the null space of a of t. You may have other equilibria. If you had another equilibrium away from 0, what's its relationship with 0? So let's just think geometrically for a point. For the question I'm asking, let's think about a state space which is R2. I'm saying that 0 is always an equilibrium point. That's because if you plug in 0 on the right-hand side, x dot is always 0. So it's a point of rest. You're not going to, once you get to 0, you're not going to, if you get to 0, you're not going to move from 0. But now I said I've got, say I have another equilibrium point here, xe, which is not 0. And my question was, what is the relationship, maybe a geometric relationship between that equilibrium point and 0?
There has to be a straight line because of null space.
There has to be a straight line because of what we know about the null space. So if xe is in the null space is a subspace, so that has to be all of, if that's a non-zero equilibrium point, all of the points along here have to be non-zero equilibria. So this is a line, we'll call this a line of equilibrium. Interestingly, that's one of the defining characteristics of a the knot of this is one of the defining characteristics of a nonlinear system. Nonlinear systems can have multiple isolated equilibria, meaning that you can put a ball around it. If it's an equilibrium, you can put a ball around it and there's no other equilibria inside. For linear systems, you can't do that because of that nice linear structure, the subspace structure of the null space. For a nonlinear system, it's a preview of 222 for those of you who are going to take it. For a nonlinear system, you're just looking for zeros of that function. So you don't necessarily have such a nice, you don't have a nice linear structure.
You're saying that those in nonlinear systems, like the stability points don't have to be connected.
The equilibrium points, yeah. The points of equilibrium don't have to be connected to each other. Okay, so now, based on that definition of equilibrium, we define internal stability in terms of an equilibrium. So we could have an equilibrium, we could have another equilibrium. If we do, we have a line of equilibrium. But for now, let's just focus on the equilibrium that we always know is at 0. And let's talk about the stability of the system in terms of the stability of that equilibrium point, which is really how we define the concept, the general concept of stability. So we say that xe equals 0, it's the n-dimensional 0, is stable. So just by definition, what does it need to be stable? It means that for all initial conditions, for all initial times, the map or the function which gives us the state trajectory, which is phi of t comma t equals 0 at 0, is bounded. All t greater than or equal to 0. Okay, so it doesn't actually require us to have a trajectory which converges to the equilibrium point. It just has to stay bounded. So it's kind of a loose definition for stability. And we want that because sometimes we care about systems being stable. We don't necessarily want them to converge or need them to converge to an equilibrium point, but we care about them being stable. When we do care about more things, so now suppose we want it to either get close or get close with a known rate to the equilibrium, less than or equal to. So let's just take the norm of both sides of this. The induced norm of e to the at times the norm of x0. So we know that just from this expression here. Okay, so you can kind of see what we need to show here. All right, so let's be careful about this. So basically I'm interested in the norm of e to the at, and I want to be able to show that that norm is bounded by this decaying exponential. Well, if A is diagonal, or if A is diagonalizable, now I'm going to use diagonal and diagonalizable, they're sort of equivalent because if it's diagonalizable, there's a similarity transform, and that similarity transform just, it just adds constants to a norm, right? We can just immediately put it into diagonal form and use that. So if I've got the diagonal case, so we're just going to recall the diagonal case. So we know then that e to the at is equal to, let's just write it in terms of the dyadic form, summation from I equals 1 to n of e to the lambda I t times this rank 1 matrix, which is formed from the left and right eigenvectors, BI transpose. So this was what we called Ri, a rank 1 matrix. And it's a constant, right? It's a matrix whose elements are constant. All right, so you see there's kind of hope. If A is diagonalizable, then e to the at just looks like that, right? So take its norm, and you immediately can see this norm is going to be constant, and then we have norms of e to the lambda it. Okay, so if lambda i's are all in the left half plane, then voila, you have your decaying exponential, which is going to be bounded by the eigenvalue that's closest to the j omega axis. Let's see that a little more carefully, but before we do that, let's just look at the Jordan form. So, so not diagonalizable, I'll just write this Jordan form. So this is a little harder, right? Or it's a little more complicated. We don't have this nice dyadic form, but we have something that's, you know, it's okay. It's the summation from I equals 1 to n. I may have repeated I will have repeated eigenvalues, but I'm going to split them up there. And then there's going to be, I'm still going to have an e to the lambda it here for each of the eigenvalues. But now I don't have these constant matrices. The kinds of matrices that I have here are things that look like Jordan forms where the e to the lambda its have been taken out. So for example, we'll have things like, you know, maybe there's a Jordan form up here associated to lambda I. So I'll have a 1, 1, t, 0, and then the rest will be, everything else will be 0. Or I might have, you know, something like e to the lambda it. Let's pull out another one. So maybe down here I have a Jordan form where I've taken out the lambda i's, e to the lambda it off the diagonal, but now I'm going to have my you know, t's here, and then I'm going to have my t squared over 2 factorials here, etc. Right? So, and a t. So we're going to have matrices that are multiplying my e to the lambda it's, which are not constants anymore. They have t in them that come from the Jordan blocks. All right. So in general, the way that we write the expression of e to the at, remember Jordan form is our general form, so we write the expression of e to the at as follows. E to the at is equal to the summation from I equals 1 to n of pi k of t e to the lambda it. In this case, I put the scalars lambda I afterwards, where these are polynomial, they're matrix polynomials in T. They're going to have terms like t cubed, t squared in them, depending how big your Jordan blocks are associated to each eigenvalue. Okay, so each of these pi k of t's are n by n matrices whose elements have, they're dependent on time, they're polynomials in time. And that just comes from what we know about the Jordan structure. Does everybody see that? Because now that we've got this form, we're fine, because exponentials decay faster than polynomials grow. And that's the key. But that's really, we need it. It relies on using this general representation of e to the at. And I think this is probably a very useful thing to really understand and remember, is that generally e to the at always looks like this. We can always take a square matrix and put it in Jordan form. So we always have this form where these are the exponentials and those are polynomials, but they're matrix polynomials in time. And now we're set. Now we can do, well, not everything, but we can now follow this. Yeah.
So we're assuming, because we want to express in the most general case that, like, of the two, the case 1 and case 2, we're taking the chord in one because we don't know if it's diagonal.
Well, that's true, but the diagonal case is a special case of the Jordan form, right? In the diagonal case, these don't depend on time, they're just constants. They're matrices with constants, like, you know, we know exactly what they are. Okay, so this is always true. All right, now going back to what we want to do, now we can just move forward with this. So norm of e to the at is less than or equal to summation from I equals 1 to n of norm of pi, that should be pi I. Sorry, I'm mixing up my i's and k's, so I use k as the index in the notes on the board. I don't know why I'm doing that, but we'll follow through. So that's pi I of t, and this is, and now I'm taking the norm of this, so the imaginary component, so lambda I may be complex, but the imaginary component in the exponent doesn't add any, it has norm 1, if we compute that norm. So we just get e to the real part of lambda I t. That's the real part of lambda times, the real part of lambda I times t. And now I'm just gonna say, okay, so that's a matrix norm. You know, all I know, whatever norm I use is what I'm gonna get out is a polynomial in time, because the things inside that matrix, the entries of that matrix are polynomials in time. So whatever matrix norm I choose, that norm is gonna give me some scalar polynomial in time. So that's, and so what have we done here? That's less than or equal to. So I'm gonna wrap up a few steps here and just write that as p of t e to the minus mu t, where p of t is, where p of t bounds is an upper bound, the norms of, I'll write it out, it bounds pi I of t norm, and is a polynomial. And mu, it represents the largest eigenvalue that I have. So mu is negative max of the real part of lambda k, lambda I, where lambda I is an eigenvalue. Alright, so what does this mean here? So I've chosen mu so that it's, so these are the eigenvalues, so this is lambda 1, lambda 2, lambda 3, lambda 4. Mu has to be chosen to be this one here, or the real part of this one here. Mu is equal to the real part of, or it's negative the real part, negative the real part of lambda 3, the one that's closest to the j omega axis, the slowest one to decay. Okay, so I've replaced that. So how did I do that? I did several steps in here. This was a summation. Each of these had real part of lambda I. So I basically did two things. I replaced this with something that bounds the sum, and then I replaced this in each of the elements of the summation with the largest one. And then that allowed me to pull them out of the summation and just get some expression for the bound. Okay, so now I'm almost there, right? Because I have a bound which is a decaying exponential bound on norm e to the at. But we have to just take a look at this. So what I said earlier, this is a polynomial in time, and this is an exponential in time. So this is growing in time, and this is decaying in time. if mu is positive. Mu is defined to be positive because it's negative the real part of a negative number. All right, so because P of t is a polynomial, I know that for all positive epsilon, there exists some positive number, which is a function of epsilon, such that I can bound the absolute value, it's just a scalar, the absolute value of P of t to be less than, to be between 0 and this m of epsilon e to the epsilon t. Okay, so what I'm stating here mathematically is that polynomials grow slower than exponentials. So now I can look at this expression, I can replace P of t while maintaining that bound with the exponential bound, and I just have to make sure that it's true for all epsilon, so I'm just going to choose epsilon to keep the overall bound of mu minus epsilon to be negative, so that I still get an overall decay. So basically I have to choose epsilon in this region here. Choose the absolute value of epsilon to be less than mu. Okay, so from this, I have that the norm of e to the at is less than or equal to m e epsilon e to the minus mu minus epsilon t. And I'm going to choose epsilon to be less than mu such that mu minus epsilon, which I'm going to call alpha, is greater than 0. All right, and now we're there. Now we've got a decaying bound, a decaying exponential bound. So going back to where we were over here, we needed to show that x of t is bounded above by a decaying exponential, because we know that the norm of x of t is bounded by this. Now, if we just take our bound on norm e to the at and plug it in, we've got the decaying exponential bound that we wanted. All right, so we did it carefully. We went through that carefully to and where were we careful? We were careful in thinking about the Jordan form and how we translate our representation of A in Jordan form to a representation of e to the at in terms of polynomials times decaying exponentials. And then the rest is just being careful about establishing the bound correctly. This is an if and only if proof. So we've shown now, we showed that if all of the eigenvalues are in the open left half plane, then the system is exponentially stable. So we proved this direction. To prove the other direction, so the other direction is that exponential stability of the equilibrium implies that all of the eigenvalues of A are in the open left half plane. Again, we can prove that direction by contradiction, or contrapositive. So if at least one of the eigenvalues of A, so if this does not hold, then that proves that this is not exponentially stable. And that direction is fairly easy to do, so we will prove that, well, it's more straightforward than I think the direction that we just proved, but to prove this direction, we'll do contrapositive. So we'll prove that so the knot of the spectrum being in the open left half plane implies that the system is not exponentially stable. So now this is fairly straightforward, because if all of the eigenvalues are not in the open left half plane, it means that at least one of the eigenvalues is either on the j omega axis or in the right half plane. And as soon as you've got that, just now look at your expression for e to the at. So we have by our hypothesis at least one lambda I belonging to the spectrum of A is not in the open left half plane. Therefore, nice useful expression for e to the at, summation from I equals 1 to n of pi I of t e to the lambda I t. Just plug in that lambda and e to the at is going to go off. Or it's not, I mean, even if lambda I is on the j omega axis, this is not going to decay to 0 anymore. And so there's no way that this is going to decay to 0. Norm x of t is not less than or equal to m x 0 e to the minus alpha t for any m. All right, so for a linear time invariant system, if all of the eigenvalues are in the open left half plane, we have exponential stability. Picking up on something we said in last day's class when we were sort of talking about intuitive notions of, you know, where the placement of the eigenvalues of A, how that relates to the stability of the system, I'd now like you to go through and use maybe use the similar ideas of what we've just proven to prove the following. So not asymptotic stability, not exponential stability, which are the same in the time invariant case, but just stability, internal stability. Stability of this equilibrium xe at 0 of this linear time invariant system. Just go through and prove our hypothesis from last day, that x equals 0 of x dot equals ax is stable if all of the eigenvalues of A are in the closed left half plane. Okay, so that's what we call C minus. So that means you can include the j omega axis, but each j omega axis eigenvalue has Jordan block of size 1. So you're allowed, in the case for stability, you are allowed to have eigenvalues on the j omega axis. So that would have 0 real part here. But that better have a Jordan block of size 1, or you're going to get some t's appearing over here. Right? So think of this notion of e to the at, and just go through that proof. Make sure you understand how that works. All right, so we talked about equilibrium. We talked about 3 notions of stability: stability, asymptotic stability, exponential stability. We discussed how, for linear time invariant systems, asymptotic and exponential stability means the same thing. So you only differentiate in time for linear systems in time varying cases. And then we proved the probably the most useful or the most widely used notion of our test for stability of linear time invariant systems, which is a test on the eigenvalues. And we've got kind of this graded form that if the eigenvalues are in the open left half plane, then the system is, the equilibrium at 0 is exponentially stable. If you have some eigenvalues on the j omega axis, you're never going to be exponentially, you won't be exponentially stable, but you still may be stable if those eigenvalues have a Jordan block of size 1 associated to them. So what's the connection now back to, between what we've done so far in internal stability, back to bounded input, bounded output stability? So the result is that, or the connections between BIBO stability and state space, or internal stability, are kind of neat, and we implied them last day when we did a few examples. But internal stability, in internal stability we've focused on, let's just write it out as a time invariant system, but we focused on the relationship of the state to the matrix A. Now we're going to put an input in, and we'll put an output in too. And so if we know that this system here is exponentially stable, then we know automatically that our input-output system will be bounded input, bounded output stability. So exponential stability of the equilibrium of x dot equals ax implies bounded input, bounded output stability of L, where L is this whole system. But the reverse is not necessarily true. And the reason is that you can have a system that's bounded input, bounded output stable because some unstable eigenvalues, some eigenvalues in the right half plane, say, may be hidden because of the relationship of B and C in the input-output response. Okay, so we did example 1 last day, but let's look at an example of this. So suppose you had a matrix A, which was, this is the example from last day. And I'm just going to change the eigenvalue at -3 to an eigenvalue at 3. All right, so from what we've just done today, we see that that system is not, well, it's not even stable. If we think about the internal stability. However, I've set up B, because it's a diagonal system, I can just put a 0 here and I know I'll get rid of that unstable eigenvalue in the input-output response. And here's a C. And we've computed the transfer function h of s, which is C si minus a inverse B. There's no D. And if you go ahead and compute this, you see that though the system itself has an eigenvalue at 3, that eigenvalue at 3 is hidden in the input-output response. So the only eigenvalues that appear in the transfer function are the eigenvalues at -1 and -6. So if you couldn't see the state, and you could only see the system from its input-output response, you'd say that's a stable system. But it's only BIBO stable. It's not internally stable. BIBO, but not internal. And I put in a third example where I just did the same thing, but just to illustrate, so I'll just put this in blue here. In the third example, I put that value back. I kept the A matrix the same, but now I put a 0 down here. And again, when you calculate the transfer function, well, you get the same transfer function. And again, so in this case, the system is BIBO stable, but it's not internally stable again. The reason it's BIBO stable when the original system is not internally stable is because that eigenvalue at 3 is hidden from the output. in the previous case, the reason that it was BIBO stable but not internally stable was because that eigenvalue at 3 was not affected by the input. So there's two ways that you can have hidden modes. It can be modes or eigenvalues that are not affected by the input, or they're hidden from the output. Okay, so when you hear the term hidden modes, it basically means that you've got eigenvalues in your matrix A, which, because of the algebra of how A is linked with C and B, those eigenvalues don't appear in the input-output response. And where it's interesting, actually, is when there are unstable eigenvalues that are hidden from the input-output response. That's usually a problem. Because, even though your input-output might be nice, something's going haywire in the internal system. Okay, so in summary, we've talked about bounded input, bounded output stable. We've talked about internal stability. We defined equilibria, and we've developed a few tests for both BIBO stability and then for the linear time invariant case for internal stability. And then we studied a little bit the relationship between the two through some examples. Where we're going now on next week is we'll spend a little bit more time on stability, talking about the concept of Lyapunov stability for linear systems. And then we'll move on and start talking about control structures. So now we have a goal of something that's good, stable systems. And we're going to use that goal to motivate design of controllers to try to stabilize systems. You've seen little bits and pieces of control design so far in the course. Now we're going to bring that together and synthesize that. Kind of the last main unit of the course. All right, so as I said, I have a couple of stability problems. It's not going to be very long homework, but homework 7 will be posted tonight, and we'll make it due next Friday. Have a very nice, long weekend.